Continuing on with my reading, the principle of Galilean relativity. To describe a physical event, we must establish a frame of reference. You should recall from chapter 5, we haven't read that yet, that an inertial frame of reference is one in which an object is observed to have no acceleration when no forces act on it. Furthermore, any frame moving with a constant velocity with respect to an inertial frame must also be an inertial frame. That sounds a little weird, but basically, imagine you have a GoPro attached to your forehead. As you run with that GoPro, the video it records will be exactly what your eyes see. So this inertial frame is kind of a way of positioning your own coordinate system, and it's inertial. Some stuff related to acceleration, related to forces. I'm not too sure how to simply explain that, so we'll just keep reading. There is no absolute inertial reference frame. That sentence alone is crazy. I actually think it is a pretty important sentence. We'll see later why. Let's try to figure out what that sentence even means. I'm saying that because my idea of an inertial reference frame is just kind of shaky at the moment. Therefore, the results of an experiment performed in a vehicle moving with a uniform velocity must be identical to the results of the same experiment performed in a stationary vehicle. The formal statement of this result is the principle of Galilean relativity. The laws of mechanics must be the same in all inertial reference frames. Okay, so that word, that series of words, inertial reference frame, it just comes up over and over. Like we've seen it 3 times in 3 different paragraphs here. So it's an important thing, and I'm gonna maybe just take a quick note in my mind or on a notebook near me. Inertial reference frame and also Galilean relativity. Those 2 big things. If I'm just chilling out later in the day and I have nothing to do, I'll be like, what does that mean? Can I explain it to myself simply? Maybe I'll take some Wikipedia, ChatGPT searching, find another YouTube video online talking about Galilean relativity or inertial reference frames, because they're complicated ideas. Yeah, so take a note of that. Take a note of some other things I may have missed as well, and let's keep reading. Let's consider an observation that illustrates the equivalence of the laws of mechanics in different inertial frames. The pickup truck in figure 39.1 moves with a constant velocity with respect to the ground. Here it is. Figure 39.1. If a passenger in the truck throws a ball straight up, and if air resistance is neglected, the passenger observes that the ball moves in a vertical path. The motion of the ball appears to be precisely the same as if the ball were thrown by a person at rest on Earth. The law of universal gravitation and the equations of motion under constant acceleration are obeyed whether the truck is at rest or in uniform motion. Interesting. So basically it's saying, just like the idea of the GoPro on your head while you're running, if you're just sitting in your room or out in a field and you throw a baseball or you start juggling, you're sitting there and your surroundings are the inertial reference frame, like the room in your floor or the ground of the field you're standing in. But as soon as you go in a car and you start accelerating and you get some kind of velocity, so there's 2 things you could be doing. Either a constant velocity, like let's say you're moving 5 kilometers an hour forward, pretty slow, constant velocity, or you could be accelerating, which is like each second you get faster and faster. Those 2 things are important because remember Newton's second law, F equals ma. If a is acceleration and a equals 0, then force on the other side equals 0. So without acceleration, there's no force. This is why when you speed up or slow down in a car, you feel that like yeet in the back of the seat. That is a force due to the acceleration. But as soon as you pick up the pace in the car and you get to like 100 kilometers an hour and you're just cruising, like you're not speeding up, you're not slowing down, you're just chilling at a constant velocity, 100, then you don't feel those forces. So there's a slight difference there that I want to make apparent because it is pretty important. That's this constant acceleration thing that they're talking about. Anywho, main picture here, laws of physics follow the same thing in all inertial reference frames. So if the girl standing outside on the ground juggles the ball, it'll follow the same kind of like kinematic classical mechanics physics as if the dude in the car did the same thing. I hope that makes sense. Let's keep reading. Consider also an observer on the ground as in figure 39.1, the girl. Both observers agree on the laws of physics. The observer in the truck throws a ball straight up and it rises and falls back into his hand according to the particle under constant acceleration model. That's just some classic mechanics kinematics. They actually said over here in chapter 5, so if you're interested, I haven't done a course on this chapter 5 stuff, but that is kind of the foundations that relativity picks up on. Do the observers agree on the path of the ball thrown by the observer in the truck? The observer on the ground sees the path of the ball as a parabola, as illustrated in figure 39.1. Here. Figure 39.1b. Whereas mentioned earlier, the observer in the truck sees the ball move in a vertical path. Furthermore, according to the observer on the ground, the ball has a horizontal component of velocity equal to the velocity of the truck. Makes sense. And the horizontal motion of the ball is described by a particle under constant velocity model. Okay, interesting. Although the two observers disagree on certain aspects of the situation, they agree on the validity of Newton's laws and on the results of applying appropriate analyses that we have learned. So this is talking about the kinematics you learn with Newton's laws in classical mechanics. You break down his particle under acceleration, which is like the force of gravity. The force of gravity is a force. It creates an acceleration. That's why things fall and they accelerate down towards the ground. But if you're in a truck going a constant velocity, you can apply the constant velocity model, which is A equals 0, no acceleration because you're going at a constant velocity. Force equals 0, 0 force, but a constant motion. So you can apply some kinematics equations there and figure out what happens. This agreement implies that no mechanical experiment can detect any difference between the two inertial frames. The only thing that can be detected is the relative motion of one frame with respect to the other. This is super interesting. And you might be wondering, like, what is going on here, bro? This is relativity. Like, why are they talking about all these frames of reference? Why are they bringing up Newton? It's a little weird, but it's like setting the groundwork for what the theory is. Let's take a look a little bit forward to see how much we have left of this section. I think if we finish everything related to this section here, we will have a strong grasp of relativity. Let's check out this quick quiz. Quick quiz 39.1. When an observer in figure 39.1, this figure here, sees the ball's correct path, which observer in figure 39.1 sees the ball's correct path? A, and correct is in italics. Interesting. A, the observer in the truck. B, the observer on the ground. C, both observers. I mean, you can't really pick A or B. Observer on the truck, observer on the ground. Like, what is the difference? The observer in the truck sees the ball's correct motion relative to him. He throws it up, it goes down. Regular standard scenario. He's just in a car, which is a bit weird. But if the girl standing on the ground throws the ball up and down, she would see it exactly like how the dude sees it in figure A if he's in the truck. But if she is on the ground and he is in the truck and he throws the ball up and down, to her, the ball would go in a parabolic shape because he's moving. So it looks like they both see the correct path. I'm gonna lock in both, and I'll post the answer of the quick quiz up here. Hopefully it's good. So let's keep reading. Suppose some physical phenomena, which we call an event, occurs and is observed by an observer at rest in an inertial reference frame. The wording "in a frame" means that the observer is at rest with respect to the origin of that frame. The event's location and time of occurrence can be specified by four coordinates: x, y, z, t. We would like to be able to transform these coordinates from those of an observer in one inertial frame to those of another observer in a frame moving with uniform relative velocity compared with the first frame. Man, that was a lot of words and very big sentences, and they were confusing, but take a look at this image. This image is talking exactly about the paragraph that we just read. An event, which is a thing you're going to see a lot in this chapter, events. This event occurs at a point P. So this point has x, y, z coordinates, and it also occurs at some specific time. That's what an event means, this thing with all of these coordinates. The event is seen by two observers in inertial frames S and S prime, where S prime moves with a velocity v relative to S. So these coordinate systems, you could label one of them, which is like kind of chilling, not moving at all. You can label that one S. And then there's one S prime, which has an imparted velocity v with respect to reference frame S. So you can kind of apply this figure here, 39.2, exactly to this. So one reference frame is the girl standing on Earth. I would argue that the girl standing on Earth is this constant reference frame with no velocity. And then the other reference frame is this dude in the car. And I would argue that this dude in the car can be described by reference frame S prime because reference frame S prime has this imparted velocity v with respect to the unmoving reference frame S. So that velocity v, you could call it the velocity of the car or the truck. And this event that's happening in reference frame S, let's say, is the guy throwing the ball up and down. So this paragraph here is kind of setting up mathematically how you can talk about different reference frames and different observers seeing different events. Okay, keep that in mind and maybe reread it a couple more times. It is a bit confusing first time you read it, but let's keep going. Consider two inertial frames S and S prime, figure 39.2. Okay, it's probably going to say exactly what I said here. The S prime frame moves with a constant velocity v along the common x and x prime axes. So you have two x-axes here. The prime is associated to the S prime moving reference, and the unprimed is associated to the non-moving reference frame. Where v is measured relative to S. Okay. So velocity of the S prime frame measured with respect to S, the unmoving frame. We assume the origins of S and S prime coincide at t equals 0. Interesting. So the reference frames start at the same point, and then since one is moving, it gets further and further from the other because the other is not moving. And an event occurs at point P in space at some instant of time. For simplicity, we show the observer O in the S frame and the observer O prime in the S prime frame as blue dots at the origins of their coordinate frames in figure 39.2. So we have just the origin with a blue dot there representing the observer. And there's an observer in each scenario. The person standing on the ground, unmoving reference frame, and the person standing in the car, moving reference frame. We label the observers as blue dots at the origin of their coordinate frames in figure 39.2, but that is not necessary. Either observer could be at any fixed location in his or her frame. Cool. That's good to know. Observer O describes the event with space-time coordinates x, y, z, t, whereas observer O prime in S prime uses the coordinates x prime, y prime, z prime, t prime to describe the same event. Model the origin of S prime as a particle under constant velocity relative to the origin of S. Okay, this is applying some kinematic stuff from the chapter 5 that was mentioned earlier, some of Newton's equations. As we see from the geometry of figure 39.2, the relationships among these various coordinates can be written as boom. And basically we have y prime equals y, z prime equals z, t prime equals t. The only difference is x prime, the x coordinate of the event with respect to the s prime observer, is a little different. It is the exact coordinate x as measured by the O observer in the non-moving reference frame, and you subtract this little vt. So the way that works is they talk about the geometry here. So we have vt, which is the distance that the S prime frame has moved from the S frame. So remember they said at point t equals 0, the origins O and O prime coincide. They're at the same point. But since we have S prime with some velocity v, after a certain amount of time t, it's going to have moved a specific distance. So velocity has units meters per second, time has units of seconds. If you multiply meters per second times seconds, you get meters, which is a distance. So this vt is a distance, the separation distance of the two frames that we're talking about. X is the position of the event P with respect to the unprimed reference frame, and X prime is the position of event P with respect to the primed reference frame. So you can see that x is equal to vt plus x prime. And using that, you can derive this equation here. Since the velocity is only in the x direction, then the Galilean transformation equations only show a difference or a transformation in the x direction. So I know that might be a lot. These are the Galilean transformation equations. You'll see that this buildup slowly leads into the Lorentz transformation equations, which are pretty much the foundation of like relativity. That's what we're going to use in this entire chapter. But to kind of understand what's happening, I would say spend a bit of time in this section here and try to explain to yourself what these things mean. Remember before we saw that an important thing we read was principle of Galilean relativity? Take a look also at Galilean space-time transformation equations and see if you can kind of make sense of those in your own way. Basically, there are ways of relating two different reference frames. Cool. These equations are called the Galilean space-time transformation equations. Note that time is assumed to be the same in both inertial frames. This is a crazy sentence, this one. And by the end of this chapter, you're going to see that this is actually not true in relativity. I'm going to just leave it at that little cliffhanger. That is, within the framework of classical mechanics, all clocks run at the same rate, regardless of their velocity. A little bit of a foreshadowing there. So the time at which an event occurs for an observer in S is the same as the time for the same event in S prime. Consequently, the time interval between two successive events should be the same for both observers. Although this assumption may seem obvious, it turns out to be incorrect in situations where v is comparable to the speed of light. Crazy. Now suppose a particle moves through a displacement of magnitude dx along the x-axis in a time interval dt as measured by observer in S. It follows from equation 39.1, the Galilean transformation equations over here, that the corresponding displacement dx prime measured by an observer in S prime is, and then they show you kind of like the calculus or infinitesimal version of those equations, where frame S prime is moving with speed v in the direction x relative to frame S. Because dt is equal to dt prime, we find that, and then they give you some kind of velocity equations here. And they also relabel velocity as u subscript x. That is because dx by dt is defined as velocity. They actually tell you that here, where u subscript x and u subscript x prime are the x components of the velocity of the particle measured by observers in s and s prime respectively. So velocity in x direction as measured by observer in s, velocity in x direction as measured by observer in s prime. We use the symbol u rather than v for particle velocity because v is already used for the relative velocity of the two reference frames. Interesting. So we just introduce a new symbol here because, we're talking about a little bit more complicated theory than the Newton's equation. So we just incorporate a new symbol for velocity because we've already used velocity somewhere else in our theory. Awesome. Equation 39.2 is the Galilean velocity transformation equation. Cool. It is consistent with our intuitive notion of time and space, as well as with our discussions in section 4.6. I haven't read that. As we shall soon see, however, it leads to serious contradictions when applied to electromagnetic waves. Interesting. Okay, a lot of crazy stuff just in this series of 3 or 4 paragraphs. What can we read? So we have the speed of light left. We have a quick quiz, pitfall prevention, a picture, and then the speed of light has 1, 2, 3, 4, 5, 6, 7, 8 paragraphs, and then we finish. So I do want to read all of this up to section 39.2 in this video, but I want to just slow down a bit and let's read this pitfall prevention. It might help us a little bit. Pitfall prevention 39.1. The relationship between the S and S prime frames. Many of the mathematical representations in this chapter are true only for the specified relationship between the S and S prime frames. The X and X prime axes coincide, except their origins are different. The Y and Y prime axes and the Z and Z prime axes are parallel, but they only coincide at one instant due to the time-varying position of the origin of S prime with respect to that of S. We choose the time t equals 0 to be the instant at which the origins of the two coordinate systems coincide. If the S prime frame is moving in the positive x direction relative to S, then V is positive, otherwise it is negative. That pitfall prevention was a bit confusing, but basically it's saying these equations are only true because we've set up our picture exactly like this. If the reference frames are moving in a crazy pattern with respect to each other, then these equations here become a little more complicated. But these equations here you can apply to this scenario because the two reference frames are just moving in the x direction. If the car started moving everywhere or it started going up in the z direction, like it started flying, then the reference frames would be moving really weird with respect to each other. So the transformation equations would look very weird as well. But in this class, we're going to start off with this because, start off with the simplest case and then apply it to more complicated cases later. Anyway, let's read the quick quiz here. Maybe we can do this one if we can. A baseball pitcher with 90-mile-an-hour fastball throws a ball while standing on a railroad flat car, moving 110 miles an hour. The ball is thrown in the same direction as that of the velocity of the train. If you apply the Galilean velocity transformation equation in this situation, is the speed of the ball relative to the Earth 90 miles an hour, 110 miles an hour, 20 miles an hour, 200 miles an hour, or E, impossible to determine? Okay, let's just take a look at the numbers. So we have a baseball thrower. He throws a ball at 90 miles an hour, and he is standing on a flat car which is moving 110 miles an hour. He throws the ball in the same direction as the velocity of the train. So imagine you are in this scenario here, and instead of throwing the ball up here, you throw it directly forward. What does the person on Earth observe? That's why they ask you for the speed of the ball right here relative to the Earth. So the way I'm doing this, just kind of intuition, 110 plus 90 gives you 200. That is my intuition. You could use these equations here, right? So velocity of the reference frame here, V, is 110 miles an hour, right? Because Earth is staying still, and the train, which is where the pitcher, the second dude, is standing, is moving 110. So V is 110. The moving reference frame is U prime. So the velocity in the moving reference frame is 90, right? Because the guy throws the ball, he's in the moving reference frame, which is denoted by the prime. So he has 90. And what we're looking for is actually u subscript x, the speed of the ball relative to Earth, right? And Earth is not moving. That's why it is defined by the unprime reference frame, right? I'm just going back to this picture here. The non-prime reference frame is not moving. The prime reference frame is moving. So technically, using this equation is exactly what I did intuitively in my head. I just move the minus v over here to the other side, which gives me ux prime, which is 90, plus 110, which is the v, equals ux, which is 200. So I don't know if that's right. I'm going to put up the answers here. That is my point there. Let's move on and quickly read through the speed of light, because I think this is going to fit everything together for relativity. It is quite natural to ask whether the principle of Galilean relativity also applies to electricity, magnetism, and optics. Interesting. We literally just came from this boat, so let's see if we can understand something from the optics perspective. Experiments indicate that the answer is no. Brother, what? Recall from chapter 34. I don't know if we read that. Maybe I looked at that in my previous semester, but I can't remember 34. Anyway, Maxwell showed that the speed of light in free space is 3 times 10 to the 8 meters per second. Physicists of the late 1800s thought light waves move through a medium called the ether. I do remember looking at the ether. The Michelson-Morley experiment, I think, did an experiment to see if there was an ether. And the speed of light is c only in a special absolute frame at rest with respect to the other. Okay, this is a crazy sentence. The speed of light c is only in a special absolute frame at rest with respect to the ether. Okay, this is a crazy sentence. Ponder it a little bit. I'm not going to go too deep into it, but I'm just kind of outlining it here as a super important sentence. Maybe I'll note it down and then later take a look and be like, what does this sentence mean? The Galilean velocity transformation equation was expected to hold for observations of light made by an observer in any frame moving at speed v relative to the absolute ether frame. That is, if light travels along the x-axis and an observer moves with velocity v along the x-axis, the observer measures the light to have speed c plus or minus v, depending on the directions of travel of the observer and the light. Okay, so they're basically applying these equations here with the quick quiz that we just did, except with the speed of light. Like imagine instead of this guy throwing a fastball, he just turns on a flashlight while he's going on a flat car this speed. So then they're saying, okay, the speed that is emitted by the flashlight is of course going to be c plus or minus the speed of the car, plus or minus depending on if the guy shines the flashlight forwards or backwards, depending on the directions of travel of the observer and the light. Makes sense. Because the existence of a preferred absolute ether frame would show the light is similar to other classical waves and that Newtonian ideas of an absolute frame are true, considerable importance was attached to establishing the existence of the ether frame. So the ether right now is like a theory. They're like, okay, maybe there's an absolute frame of reference. We'll call it the ether, and they're trying to find it in the 1800s, right? That is from this sentence kind of onward. Prior to the late 1800s, I'm now reading over here, experiments involving light traveling in media moving at the highest laboratory speeds attainable at that time were not capable of detecting differences as small as that between c and c plus or minus v. Starting in about 1880, scientists decided to use the Earth as the moving frame in an attempt to improve their chances of detecting these small changes in the speed of light. Observers fixed on Earth can take the view that they are stationary and that the absolute ether frame continuing the medium for light propagation moves past them with a speed v. Determining the speed of light under these circumstances is similar to determining the speed of an aircraft traveling in a moving air current or wind. Consequently, we speak of an ether wind blowing through our apparatus fixed to the Earth. I'm not sure if this is making too much sense, but we'll just keep reading until maybe something clicks. A direct method for detecting an ether wind would use an apparatus fixed to the Earth to measure the ether wind's influence on the speed of light. If v is the speed of the ether relative to the Earth, light would have its maximum speed c plus v when propagating downwind, as in figure 39.3a. So here's figure 39.3. We have a bunch of different images here. A is the one over here. The speed of light is c plus v in the downwind direction. So we have c. They're saying that this ether has a velocity v, and the total observed speed of the light should be c plus v, right? The speed of light plus this additional ether that is kind of pulling it towards whatever direction it's going. Then we have the alternative scenario. The speed of light is c minus v in an upwind direction. So we have the speed of light here shining a flashlight. Maybe the flashlight is pointing in the opposite direction to the velocity of the ether wind v. Therefore, the observed velocity we get is c minus v. Let's take a look at the third scenario here. Maybe they'll talk about it. The speed of light is square root c squared minus v squared in the direction perpendicular to the wind. So we shine light at some angle over here, at some angle that is not parallel or anti-parallel to this v, and we get the observed magnitude. This picture I'm getting a little confused with. Let's read the image over here. If the velocity of the ether wind relative to the Earth is v, and the velocity of light relative to the ether is c, okay, so there, maybe I messed up some of my explanations there, but we'll keep reading. The speed of light relative to the Earth depends on the direction of the Earth's velocity. Okay, so that was a little bit of a tangent when we got to this stage here. Let's keep reading. Likewise, the speed of light should have its minimum value c minus v when the light is propagating upwind, 39.3b, we just saw that, and an intermediate value, this square root c squared minus v squared, when the light is directed such that it travels perpendicular to the ether wind as shown. But it's weird, like the angle between this c and this v is not perpendicular. Maybe they're talking about this here being perpendicular. I'm not sure. It's a little confusing here. In this latter case, so they're talking about case C over here, the vector C must be aimed upstream so that the resultant velocity is perpendicular to the wind, like the boat in figure 4.21b. This is like figure 4 is from chapter 4. I'm not going to go look at that right now. I'm just going to keep reading. If the sun is assumed to be at rest in the ether, the velocity of the ether wind would be equal to the orbital velocity of the Earth around the sun, which has a magnitude of approximately 30 kilometers per second, or 3 times 10 to the 4 meters per second. Because c is equal to 3 times 10 to the 8 meters per second, it is necessary to detect a change in speed of approximately 1 part in 10 to the 4 for measurements in the upwind or downwind directions. Although such a change is experimentally measurable, all attempts to detect such changes have established the existence of the ether wind, and hence the absolute frame proved futile. Okay, that was a strangely worded sentence, but basically they're saying that, okay, if this ether, this kind of wind or space that the light travels in actually does exist, then we should be able to measure changes in the speed of light in 1 part in times 10 in 10 to the 4. So like a super small change, and maybe like the equipment you're using isn't strong enough to measure that change, or maybe that change doesn't exist. If the change doesn't exist, then this theory of the ether wind is like incorrect. There's something wrong with it because the experiment is showing otherwise. So they're saying that all of these attempts to measure this small difference in the 1 in times 10 in the 1 part in 10 to the 4, all of them failed. So let's keep reading and see what they say over here. We shall discuss the classical experimental search for the ether in section 39.2. So 39.2 was about the Michelson interferometer. I didn't really read about that too much, but maybe now I'll go back and kind of refresh what that's about. Anyway, let's keep reading the last kind of 2 paragraphs here in this section. The principle of Galilean relativity refers only to the laws of mechanics. If it is assumed the laws of electricity and magnetism are the same in all inertial reference frames, in all inertial frames, a paradox concerning the speed of light immediately arises that can be understood by recognizing that Maxwell's equations imply that the speed of light always has the fixed value 3 times 10 to the 8 in all inertial frames, a result in direct contradiction to what is expected based on the Galilean velocity transformation equation. Interesting. According to Galilean relativity, the speed of light should not be the same in all inertial frames. Okay, so these are 2 kind of important sentences here that I would say are good to kind of reread and just ask yourself, like, what are they talking about here? Let's complete with the final paragraph of this section. To resolve this contradiction in theories, we must conclude that either 1, the laws of electricity and magnetism are not the same in all inertial frames, or 2, the Galilean velocity transformation equation is incorrect. If we assume the first alternative, a preferred reference frame in which the speed of light has the value c must exist, and the measured speed must be greater or less than this value in any other reference frame, in accordance with the Galilean velocity transformation equation. If we assume the second alternative, we must abandon the notions of absolute time and absolute length that form the basis of Galilean spacetime transformation equations. Bro, this last sentence is absolutely insane because, okay, what they're saying is we have E&M and we have Galilean velocity transformation equations, which they introduced to us here. It's literally this stuff here, which says if you're in a car and you are going a specific speed and then you throw a ball, that ball will have the speed that it is thrown at plus the speed of the car. You know, pretty intuitive, like kind of makes sense. That's why this is like a theory on its own, because people figured this out back in the day and they're like, yo, this works. But it turns out that if you apply this to E&M, which was talked about previously in chapter like 34 or something, there ends up being a contradiction that's only alleviated if we go through these 2 kind of statements here. So either the laws of electricity and magnetism are not the same in all inertial frames. So, maybe we could talk about that a bit more because it's an interesting kind of sentence. Or the Galilean velocity transformation equations are incorrect. And this is what Einstein was thinking about when he thought of this theory. So I guess this doesn't really give us a solid grasp of what relativity is, the first section, but at least it builds a little bit of a foundation. So in this experiment here, the Michelson-Morley, they actually show you that this difference, C plus V, C minus V, doesn't exist. Like, there is no ether. I think that is the conclusions of this experiment. Let's see, details of the Michelson-Morley experiment. And then Einstein's principle of relativity. Let's just check the first paragraph here. In the previous section, we noted the impossibility of measuring the speed of the ether with respect to the Earth and the failure of the Galilean velocity transformation equation in the case of light. Einstein proposed a theory that boldly removed these difficulties and at the same time completely altered our notion of space and time. He based his special theory of relativity on 2 postulates. All right, I'm going to halt it off here because we have completed like the first section in this chapter. So in the previous video, I kind of like slowly introduced this section. Maybe I read some of these paragraphs here, and then in this video, I wanted to cover the principle of Galilean relativity. So this doesn't tell you everything about the chapter, but it shows you kind of the foundational principles, like what is the problem that has occurred. And maybe, you know, you heard the word like inertial reference frame, you heard the word ether a million times, and it might not click with you too well. It doesn't click with me. Like, I'm reading some of these stuff, like especially some of these sentences here, all of this, like after the speed of light and this ending section, I read that and it didn't really make sense to me too much. So it is an interesting and kind of complicated theory to get your mind across, but this is a first introduction. So read it through, try to take a look at some of the ideas that confuse you in this section. We're going to do some problems a bit later on, but right now it's good to just absorb a lot of the theory. So next video, I think I'm going to go over this Michelson-Morley experiment. It looks like we can get through that in one video. And then I think the third video of this series, we could probably talk about the actual theory of relativity. Let's take a quick gander here. That's a pretty short section, consequences of special theory of relativity. So if you're okay with believing that the special theory of relativity is true, this section and onwards, when they talk about the consequences, like this thing over here, this is mind-bending stuff. So once we get to that, it's going to get pretty fun. But for now, you have to kind of feel what they are talking about in this section. Basically, they're talking about like different reference frames in this picture here. Take a look at this picture. This picture is going to come up a lot with these two S and S prime frames. You're going to probably do a bunch of problems where there's different reference frames moving with respect to each other. And the whole point is we have a series of equations here that relate one frame to the other, under different conditions. In this case, one frame is moving with a constant velocity v with respect to the other one, and they're moving only in the x-axis. So kind of sliding as if they were trying to model this, this kind of situation here with the car on the ball. So I hope this video was a bit helpful for you guys. Try to read through this, take a look at the quick quizzes, maybe take a look at some of the next sections. For now, I don't think you have to do any problems. Well, maybe you can hit some problems. Anyway, thank you for watching. Peace out.